If you drop a lit match into a shallow puddle of gasoline on the tarmac, it instantly erupts into a violent sheet of fire. But if you drop that same match into a pool of commercial jet fuel, nothing happens. The flame simply goes out, drowned by the heavy, oily liquid. It's a bit of a paradox. The very fluid that powers our global aviation network, carrying hundreds of people across oceans in a single bound, is remarkably stubborn when it comes to catching fire. The choice of fuel is easily one of the most critical decisions in aerospace design. It dictates the shape of the wings, the design of the engines, and whether passengers survive a landing that goes wrong. So why does the world's most demanding transport system rely on a fuel that seems to hate burning, while completely rejecting the highly volatile gasoline we put in our cars? To get a sense of what's actually going on here, we have to look at the numbers. Take a fully loaded Boeing 777-300ER getting ready for a flight across the Pacific. It carries roughly 1,280 liters of fuel inside its wings and fuselage, weighing more than 145 metric tons, nearly 40% of the airplane's takeoff weight. In the air, those twin turbofans burn through about 7,500 liters every single hour. In aviation, every gram of weight and every millimeter of space is a premium. Yet the liquid filling these massive tanks is Jet A1, a highly refined grade of kerosene. Chemically, it's closer to diesel or 19th century lamp oil than the gasoline in your car. This isn't a historical accident or a cheap compromise. It's a design choice forced by the physics of flight. To understand how we got here, we have to go back to when piston engines ruled the skies. These power plants were giant, complex versions of your car's engine, with cylinders, pistons, spark plugs, and a reliance on gasoline. At first, gasoline's high volatility was a huge plus. It vaporized easily, making cold start simple and engine response instantaneous. But as planes grew larger and faster, engineers pushed these engines to their mechanical limits, adding superchargers and turbochargers to compress thin, high-altitude air. This compression made the air hot, and mixing hot, pressurized air with volatile gasoline inside a cylinder created a thermodynamic nightmare. Instead of a controlled, smooth burn triggered by the spark plug, the fuel-air mixture would explode prematurely and violently. This is what we call engine knocking or detonation, and it's incredibly destructive. In a matter of minutes, the shockwaves could melt pistons, bend valves, and snap connecting rods right in half. To stop this from happening, fuel refiners had to create highly specialized aviation gasoline, or Avgas, raising its octane rating by adding massive amounts of tetrethyl lead. But even with leaded fuel, piston engines hit a hard thermal wall. You couldn't get more power out of them without making them impossibly heavy, complex, and prone to breaking down. The entire industry was stuck, limited by the very nature of gasoline. The breakthrough didn't come from fixing gasoline. It came from reinventing the engine. In the mid-20th century, the gas turbine, or jet engine, completely rewrote the rules of propulsion. A jet engine doesn't burn fuel in quick, explosive bursts. Instead, it operates on a continuous combustion cycle. Air is sucked in the front, compressed by a series of spinning blades, mixed with fuel in a combustion chamber, and burned in a continuous, self-sustaining flame. The expanding hot gas spins a turbine to keep the compressor running, then blasts out the back to generate thrust. Because there are no pistons, cylinders, or timed spark plugs, there's no such thing as knocking. A jet engine is actually pretty indifferent to what it burns. In theory, it can run on everything from coal dust to vegetable oil. But for commercial flights traveling at high speeds and high altitudes, engineers needed a fuel that was incredibly stable, safe, and efficient. That's why they turned to kerosene. The first major problem kerosene solves is the drop in air pressure at high altitudes. Commercial jets fly in the stratosphere, usually between 10,000 and 12,000 meters up, where the air is thin and drag is low. But at 11,000 meters, the atmospheric pressure is only about a quarter of what it is at sea level. This low pressure changes how liquids behave. Gasoline has a very high vapor pressure, meaning its molecules want to escape into the air as vapor. At sea level, that makes it easy to ignite. But up in the thin air of the stratosphere, that low pressure causes gasoline to boil at normal temperatures. If a jet ran on gasoline, the fuel would start boiling right inside the wing tanks and fuel lines. This boiling creates gas bubbles, leading to a dangerous condition called vapor lock. When vapor lock happens, the fuel pumps can't pump liquid because they're sucking in gas bubbles. The engines get starved of fuel, and you get a sudden, catastrophic flameout. Kerosene, on the other hand, has a very low vapor pressure. Its heavy molecules stay tightly bound as a liquid even in the near vacuum of high altitudes, ensuring a steady, reliable flow of fuel to the engines. This same chemical stability makes a massive difference for safety on the ground. A fuel's volatility is measured by its flash point, the lowest temperature at which it releases enough vapor to ignite. Gasoline's flash point is roughly minus 43 degrees Celsius. That means under normal conditions on Earth, gasoline is constantly venting highly flammable, invisible vapors that a tiny spark can ignite. Kerosene's flash point is around 38 degrees Celsius. At room temperature, it simply won't vaporize enough to catch fire. If an airplane leaks fuel on the tarmac during maintenance, or if there's a minor scrape during taxiing, spilled kerosene isn't going to explode instantly. You have to heat the liquid up past 38 degrees before it can support a flame. This single characteristic has saved countless lives, preventing survivable runway accidents from turning into fatal fires. Then there's the physical design of the airplane itself. To cut down on drag, modern airliners use thin, swept-back wings. These wings have to do a lot of jobs. They generate lift, support the engines, and double as the plane's primary fuel tanks. Because the wings have to stay thin for aerodynamics, the volume inside them is incredibly tight. Engineers are constantly fighting to pack as much energy as possible into this limited space. And this is where the difference between weight and volume becomes really important. If we look at energy by weight, what we call gravimetric energy density, gasoline actually has a slight edge. It yields about 44 megajoules of energy per kilogram, compared to kerosene's 43. But gasoline is less dense. It weighs only 0.72 kilograms per liter, while kerosene weighs about 0.80 kilograms per liter. Because kerosene is denser, its molecules are packed much closer together. That means when we measure energy by volume, kerosene gives us about 35 megajoules per liter, while gasoline only gives us 32. For an airliner with a fixed space inside its wings, that 8% difference is massive. It means you can pack significantly more range and flight time into the exact same wing volume. If you used gasoline, you'd either have to cut the flight short or build thicker, heavier wings that create more drag and burn more fuel. Kerosene lets designers keep the wings thin, clean, and aerodynamic, while still carrying enough energy to cross the Atlantic. But kerosene's job goes way beyond just being burned for thrust. In a modern jet engine, it actually serves a double purpose as the primary cooling fluid. A jet engine is a thermal monster. Inside its core, air is compressed to over 40 times atmospheric pressure, heating up to more than 600 degrees Celsius before it even touches the fuel. The turbine blades right behind the burner spin in temperatures that exceed the melting point of their own metal alloys. And the central shaft bearings that support these spinning parts generate intense heat from friction. To keep these bearings from failing, they need a constant flow of lubricating oil. But that oil absorbs a massive amount of heat, and if it gets too hot, it breaks down, ruins the bearings, and causes the engine to seize up. To cool the oil, engineers don't use heavy, air-cooled radiators that would ruin the plane's aerodynamics. Instead, they route the hot oil through a device called a fuel oil heat exchanger. In this exchanger, the hot engine oil flows right next to the cold fuel coming from the wings. The fuel acts as a heat sink, absorbing that thermal energy. This cools the lubricating oil back down to its safe operating range, while warming the fuel up, which actually makes it burn more efficiently once it gets sprayed into the combustion chamber. If the plane ran on gasoline, this system would be an absolute disaster. Passing volatile gasoline next to hot engine oil would vaporize the fuel instantly, creating extreme pressures and immediate vapor lock in the lines. Kerosene's high boiling point allows it to absorb this heat safely, staying liquid while keeping the engine's critical systems from overheating. If you want to understand not just what flies over your head, but why it's built that way, subscribe to Flight Simplified and stay with me. Kerosene's oily nature also solves another mechanical challenge: lubricating the fuel system itself. To get a clean, efficient burn, the fuel has to be sprayed into the combustor as an incredibly fine, atomized mist. That takes serious pressure. The fuel control unit uses pumps to compress the liquid to pressures exceeding 70 bar, which is over 1,000 pounds per square inch. At these pressures, the gears and pistons inside the pumps are under immense mechanical stress. They can't be lubricated with regular engine oil or grease, because those would wash away and contaminate the fuel. The pumps have to be lubricated by the very fluid they are pumping. Gasoline is a powerful solvent. It strips away protective oils and has almost zero natural lubricity. Running gasoline through these pumps would cause rapid wear and mechanical failure in no time. Kerosene, however, is essentially a light oil. It has excellent natural lubricity, coating the pump components, protecting them from wear, and keeping them running smoothly for thousands of hours. Of course, kerosene isn't perfect, and it has one major drawback compared to gasoline: its freezing point. When you're cruising at 11,000 meters, the outside temperature can drop below -55 degrees Celsius. Over a long flight, the fuel sitting in the wings cold soaks, dropping down toward those freezing temperatures. Gasoline has a very low freezing point, staying liquid well below -60 degrees Celsius. But raw kerosene freezes around -30, turning into a thick, waxy gel that would easily clog the fuel lines. To fix this, refiners develop specialized jet fuel like Jet A1, which is processed to lower its freezing point to -47 degrees Celsius. On top of that, aircraft are equipped with temperature sensors in the fuel tanks. If the fuel gets too cold, pilots have a few options. They can descend to warmer air, speed up to increase friction heating on the wing skins, or recirculate warm fuel from the engines back into the tanks. It's a manageable trade-off that allows aviation to get all the benefits of kerosene while keeping the fuel flowing. It's easy to think of aviation fuel as just fuel, something you burn to get from point A to point B. But in a modern airliner, it's actually an active, structural part of the whole system. It's a coolant for the engine oil, a lubricant for the high-pressure pumps, and a concentrated block of energy designed to fit into the thin profile of the wings. Kerosene is a brilliant compromise of chemistry and engineering. It trades the quick, explosive volatility of gasoline for the stable, multifunctional safety of a heavy oil. Every flight relies on this balance, turning a liquid that refuses to burn at room temperature into the very force that defies gravity. The next time you look out the window at the wing cutting through the clouds, you aren't just looking at metal and rivets. You're looking at a giant, aerodynamic fuel tank. And inside that wing, silent and invisible, that heavy oil is absorbing heat, lubricating pumps and flowing steadily, completely unfazed by the freezing, thin air of the stratosphere.